Hello and welcome once again for another ES340 video. This is day 22, part A. So we discussed vapor compression systems last time, and now we're going to discuss the other applications. So we were discussing the particular application of a refrigerator, but we can also have other applications of them, including cold storage, where you can have chilled water or making ice, these kinds of things. Cascade cycles. Well, these are examples where the idea is to actually stack multiple vapor compression units together and connecting them together in series via some other some kind of thing like a heat exchanger or whatnot. And multi-stage compression with intercooling, which is a similar kind of idea to the cascade cycles, but accomplished in a different way. So the cold storage is you can still use the traditional vapor compression system. But now, what you're going to use the use case that you're going to use is to make it as efficient as possible, economically speaking, is that you will actually first cool whatever it is, cool the water, make ice, whatever it is that you want, but you'll do that during off-peak hours. So during the night, typically, is off-peak. For power consumption when it's much cheaper. So you do the cooling or whatnot, and then you store it so that it can be used later in the day when you're during peak hours. So this is a use of vapor compression systems outside of just a typical refrigerator. Cascade cycles, as I mentioned, the idea here is to connect multiple refrigeration cycles in series. Typically it's 2, but you could imagine doing more. And now this does require more work input, right? Because we're going to have 2 cycles now that are being powered. But the idea is to try to take advantage of the cooling process that's happening in one of them for another, and this can lead to potentially beneficial results in terms of coefficient of performance. Okay, so you can in fact you could in theory get a larger coefficient of performance if this is done correctly. Now these, as I mentioned, these are typically connected via a heat exchanger. So to connect the 2 cycles, so you have one cycle and a second cycle, and the cycles, how they're connected to each other is through the heat exchanger, which happens at the condenser of one and evaporator of another, where those would traditionally be in the vapor compression system. And then multi-stage compression, another idea of connecting multiple parts. This is not quite the same as the cascade cycles, because instead of having connecting 2 refrigeration cycles here, you go through a slightly more complicated process. So notice that you go through a compressor here, then you go through a heat exchanger, and then you go through another compressor. So this is what makes this slightly different is as you go around the cycle, notice that you have this flash chamber step. Excuse me. And the idea in the flash changer is chamber, excuse me. In the flash chamber is that you will separate liquid and vapor. So basically the idea here is that you have some kind of mixture, and you're going to use this chamber in order to separate separate the two phases from one another. So then what ends up happening is you get two separate streams. You get, notice the X here. So you get the vapor stream that comes back through, and you get the liquid stream which goes down this way. So basically the flash chamber just separates the liquid and vapor from each other, and then allows them to go back through the cycle through different routes, essentially. So this is a bit different than obviously connecting directly to, because this step is what makes the key difference here, than just connecting two cascade cycles. But again, this is still a vapor compression type system, just a slightly more complicated version of that. And notice what happens here, right? So we have one that's saturated, vapor, so coming in through here. And then 2 is obviously superheated. So as I go across the compressor, what the work is getting converted to is partially converted to is superheating this fluid. And notice that this is an isentropic step, at least the ideal case, right? Is an isentropic step. Then it goes through the heat exchanger and still remains superheated. Then it goes through another compressor and remains superheated, but now again through an isentropic step across the compressor. Then when it goes through the condenser, it condenses and it becomes a saturated liquid. And then we have a step where we go, we do some kind of throttling. We come back, we go through 6 where it gets separated out, right? So the one 9 is the vapor, and 7 is the when we separate it out. 9 is vapor and 7 is so you actually have some flow going both ways, is the saturated liquid, and another throttling process from 8 to get back down to 8. Okay, at a lower temperature. So this is an example. This is obviously much more complicated, so you can imagine that if you want to figure out the efficiency and whatever, it's going to be a bit more complicated than the simple vapor compression, the regular ideal vapor compression refrigeration cycle. It's going to be a lot more analysis if that was the case, but it's a similar type of process. Now the next thing is absorption refrigeration. Now this actually differs from this process actually differs from the vapor compression type system. It has some similar kinds of details, but it also differs in the way things work here. As an example, during the the compression, step actually ends up being removed from the absorption refrigeration process, as you'll note here. There's an advantage to doing this in that the amount of work that has to go in actually decreases. So this WP dot here ends up being smaller than if I had had to use a vapor compression system. And so that's the idea, is that maybe you can squeeze out, it at least has the potential that you could squeeze out a bit more in terms of coefficient of performance, because you have to put in less work, right? You have to end up putting in a smaller amount of work. And what happens in the place of that is that actually there is a second type of, so there's one refrigerant, right? Typically something like, say, ammonia, and there's another working fluid, in this case for the absorption refrigeration, that works as the absorbent. So the basic idea is that it absorbs the refrigerant in order, when they're mixed together, in order to make a liquid solution. And the liquid solution can then be pumped, which is what the work is going to be done. Here, you can see the pump here. The liquid solution can then be pumped to higher pressure. Now, in order to then, of course, continue along this cycle, you eventually have to remove the refrigerant from the absorbent. Now, I mentioned that a common case of this type of refrigeration uses ammonia as the refrigerant, but it also uses water as the absorbent. Okay, so that's one traditional way that you can make these absorption refrigerators. Notice here that we still have the evaporator where heat comes in, and we still have the condenser where it goes out. So there are some things that are similar to the, and you go through the expansion valve effectively in between. There are some features that are similar to the vapor compression system. But notice here that there's another step here, which is a high temperature source. This is another place that can, in theory, be exploited for a better coefficient of performance. Again, obviously, when you actually get into the engineering, sometimes other things pop up, right? But the idea here is that that I have some high temperature source. Well, you notice that I'm at the condensing stage. I'm letting heat out. Well, that could be that could produce your high temperature source for this step. So it kind of so instead of exhausting that heat off into the environment, maybe you exhaust it back into the system somehow. Make sure that it comes back so that it can help produce the high temperature source. The high temperature source generally also needs some kind of input in it on its own. And what often is done is there is some kind of something that's being burnt or something like that, natural gas or something, to provide the high temperature source here in the system. So that's all that I have for this video. So this is yet another set of examples of how refrigeration is performed or could be performed in the real world.